Hello, calculus fans. Next thing we want to do is find a general method for determining if a vector field is conservative. Suppose we have a field F, which has components P and Q, and we know that this field is conservative. So for now, we're just going to talk about two-dimensional fields. Let's suppose that P and Q have continuous first-order partial derivatives. That means there is a scalar field, little f, such that big F is equal to the gradient of little f. That means that P is equal to the partial derivative of little f with respect to x, and Q is the partial derivative of f with respect to y. Now let me take you back to Clairaut's theorem, and that's the theorem that says that if we have a function with continuous second-order partial derivatives, it turns out that those mixed partial derivatives are equal. That is to say that g of xy is equal to g of yx, provided, of course, that those mixed partial derivatives are continuous. And so what that means is, if we were to take p and differentiate with respect to y, we get the partial derivative of f, first with respect to x, then with respect to y. Clairaut's theorem says that we can switch the order on taking those partial derivatives, and then that double derivative is equal to dq dx. All right, so that's going to give us a theorem. The theorem says that if you have a vector field f with components p and q, and if it's conservative, and let's also suppose that P and Q have continuous first-order partial derivatives on some domain D, then throughout that domain, we have that the partial derivative of P with respect to y is equal to the partial derivative of Q with respect to x. Unfortunately, this particular theorem goes sort of the wrong direction. It says if f is conservative, then something is true. And we really want a theorem that goes the other way. If some condition is true, then f is conservative. So the theorem, as was stated in this video, the converse of that theorem is generally not true. We're going to have to impose some additional conditions before that converse is actually true. All right, first thing, we need the idea of a simple curve and of a closed curve. Let me just give you some pictures that'll illustrate the notion of a simple curve and of a closed curve. Okay, so here's some examples. So a simple curve is something that doesn't cross itself. A closed curve is one in which the ending spot is the same as the beginning spot. And what we care about are simple closed curves. So here's the ones that we want. All right, so a simple curve can't cross itself. Closed curve must end where it begins. So we're only going to care about simple closed curves. Next thing, let's introduce the idea of a simply connected region. All right, so here's some pictures showing simply connected regions and non-simply connected regions. Now, as a loose way of thinking about it, at least in 2 dimensions, a simply connected region should not have any holes or other breaks in it. Now we are in a position to give at least a partial converse of the preceding theorem. Now this theorem is only going to work for 2-dimensional fields. Later on, we'll talk about how to handle 3-dimensional vector fields. All right, so here's the theorem. The theorem says that if we have a vector field defined on an open, simply connected region D, and that its components have continuous first-order partial derivatives, and if we know that dp by dy is equal to dq by dx, then we know that the field is conservative. So essentially, this equation right here does in fact give us a useful check to make sure that the vector field is conservative. Okay, that's all for now.